complex example on this fundamental mode design before we move on to the hazards, which we should get onto today, but another faculty member's coming in just after 12, so I'll try and complete what I can in the next 45, 50 minutes. If we don't finish, we go on tomorrow, so no problem. So I'm going to give a set of waveforms in a minute. So I'm going to draw a set of waveforms in a minute, but just to describe a problem, it's an alarm. It could be, say, an so it triggers high or low, maybe above value or below value, and it goes off. Sometime later, someone will come and press a reset button, or it could be an electronic reset, but more likely press it. So it's asynchronous. No one knows when someone's going to come. So we need to decide how long the alarm is going to sound for. So the waveform is like this. So that's that's the problem in the waveforms. So there's the alarm trigger signal, so it's just a 0 or a 1. Every time we get a changeover in the alarm, it triggers the alarm here. When you press the reset button, sometime later, we switch the alarm off. So I've missed something. So it's obvious this is the output, Z. And in this case, we've got two inputs, which I'll call X0 and X1. Okay, so first thing, remember, we've got the waveforms, but we need to assign unique states. Now, there's no tricks in this one, so let's see how we do it. Make sure I've got. So 1, 2, 3, 4, 5, 6, 7 7 level changes, and the last one takes us back, if you look at the signals, to the initial conditions 0, 0, 0. 2 notes on the input, a note on the output. So then the system can repeat. So you want to just take 2 minutes and try and do the state assignment yourself. If we start with that as state number 1, go along, tell me how many states you think the design has got. Just very quickly. Okay. Anyone got 7 states? 6? Very good. 6 is the right answer. No tricks in this one. So we just go through. You can see I won't go through it in too much detail. We did it last time. So we just step along. When there's a change in input and a change in output, clearly that's a new state 2. Then we have a change in input and a change in output, new to state 3. Then the reset signal drops out. We've got 1 note, which is the same as 1 note there, but state 2 has an output of 1, this has an output of 0, so that's a new state 4. And when this drops down here, we've got another change over. We've got 0, 0, 1. We haven't had 0, 0, 1 before, so that's a new state 5. And the last one, we've got 0, 1, 0. We haven't had that before, I don't think. So that's 6. And the last one, if you look at it, we're just back to the beginning with the alarm reset low, sorry, the alarm trigger low, the alarm reset low, and the output low. So that's just back to state 1. You all happy? Experts now? So now the next tricky stage, not so tricky, we draw the state tables, and the tricky stage is implication. And good news, we can do some minimization. So we'll draw the state tables. So 2 inputs, so 4 columns this time, and 6 rows in the table. So I'll try and draw it over here for you. Okay, so once we've drawn the tables, because we're moving between the states, you should find the next part easier. So I'll just start it, you can catch up because we're trying to push on. But the important bit is the minimization after we've got the table. So the table, we start off 0, 0 on the inputs, that's state 1, and the output there is 0. You all see that, up to there? Okay, then the next one, we go from state 1 to state 2, and input goes to 1 0, so that's into the N column. So transition state 2 points to where we're going. And the change in output from a 0 to a 1. So it means that transition state is effectively the edge in the output there. 1 to 2, so it's an unspecified state. We put it as a dash at the moment. And 2 to 3, there's another change in output. Let's go from 1 0 to 1 1. So transition state 3 to stable state 3, as an output of 0. So we need another dash in there. Effectively, this is 2 to 3 is the edge in transition in that one. 3 to 4, the output doesn't change. And then you go to 1 0. So to maintain the output low, we make that transition state 4 0. So 3 to 4, basically, we don't want any change in output. 4 to 5, the output changes again, and the input goes from 1 0 to 1 1. Sorry, 2. Should be 0 0. I missed it somewhere. Yeah, 0 0. Can't read me. 0, and 5's going out to 1, so again, there's a changeover there, so it's an unspecified state. 5 to 6, the output changes again, the input goes from 0 0 to 0 1, new state 6. The output changes from 1 to 0, so that's a don't care. The transition state 6, and finally we go back. Transition state 1, there's no change in output, so we make this transition state 0. So I'm going from 6 to 1, we maintain the output low. Everyone okay on that? Good. So now the implication table. So a lot of things to be implied here, a lot of terms. But the beauty is, all these blank spaces normally mean good news because we can combine anything with something that's empty. There's no conflict there. It's likely you can argue with a paper bag because there's nothing there, but some people manage it. So we'll draw the implication table. Have you all got this down now? So we'll leave that one up so we can see what we're comparing. Right, let's put the rules back up to see what we're trying to do. So, as we move through, if you want to refresh your memory, you can read this list. These are available probably on Friday. So, we'll start at the top, 1 and 2. Can we combine 1 and 2? Is that a yes? It's a yes. See, every column, we do it column by column. Stable state with nothing, we can combine that. 2 no entries, we can combine that. A transition state and no entry. And transition state going to a stable state, which is fine. So 1 and 2 can be combined, so we can have our first tick in the box. So it means we at least minimize one state, down from 6 to 5. But the good news is we can do more. So the next one is 1 and 3. So the first and third columns, no problem there, no problem. And the last one, you got 2 transition states, 2 and 4. So you can't make a decision on that. So that's the implication again. You need to put 2-4 in that box. So what that means is, if we can eventually combine 2 and 4, we can go back and tick that. If we can't, we go back and cross it. So the next one, 1 and 4, is even worse. 1 and 4 is the first and the fourth column, so a transition state and a stable state, 1 and 5. We can't make a decision on that, so we put 1 and 5 in the box. But there's also no problem there, no problem there, but in the final column we've got transition state 2 and stable state 4. You can't make a decision on that either, so we put 2-4 in there as well. So that now means if you want to combine state 1 and 4, both these have to be true. If one of them's true and one isn't, or both can't be combined, you have to cross it off. 1 and 5, so that's straight away you can see 1 and 5 are two stable states in the same column. Unfortunately, we've got different outputs. So we can't combine them because you can't make that as a circuit. So you have to cross out 1 and 5. And it doesn't matter about the other columns. Once you've decided on a stable state, there's no implied combination now, you just can't do it. And 1 and 6, so the top one and the bottom one. Any good news there? Yes, we can combine it. Transition state in 1, okay. Empty state in 6, empty state in 2. So we can take this, so already we've got 2 possible. And there's more. So 2 and 3 next. Unfortunately 2 and 3, everything's okay apart from a final column. We've got a stable state and a transition state. So that's 2-4. So this 2 and 4 state is becoming important. And this is bad news day. 2 and 4, 2 stable states in the same column with different outputs. We know we can't do that, so 2 and 4 are crossed off. So that means we have to cross off these as well. So we'll just do it small when you can see what's underneath. So that's killed 4 combinations basically. Well, that's life. You know, we've got more to come. Good news is following. So 2 and 5. So the second and the fifth. What can you tell me about 2 and 5? Can that be combined? Yes, because it's all combinations of empty states. So that's a tick. 2 and 5. 2 and 6. Can you tell me what that is? Well, it used to be half a crown in England when we had old money. 2 and 6. Not many people know that. So 2 and 6, yes. 3 and 4. So the third and the fourth. Yeah, we're cooking on gas now. 3 and 5. These 2. Yes. We're on solar power now. 3 and 6. Yes. A lot of ticks. 4 and 5. These 2. Yes. 4 and 6. Well, 4 and 6 is implied in this column on 2 transition states, 1 and 5. So we need 1 and 5 in there. And the last one, 5 and 6, again, is on 1 and 5. So it wasn't too bad, was it? Did you follow all this? It's quite complicated the first time, so everyone's happy. Right, so 1 and 5 cross, so we cross these off. So the final thing we do now is list out the combinations, and we have to work out the best possible groupings, which is quite difficult. So possible combinations. One and 2. 1 and 6. 2 and 3. 2 and 6. 3 and 4. 3 and 5. So now, while you're taking those possible combinations down, can anybody tell me what the best groupings might be? We've got 6 states originally. What's the minimum number of states we can get to? Well, we could decide we're going to group together states 1 and 2. That loses 1 state. States 3 and 5. That takes it down to 4 states, but is that the best grouping? It's very difficult to see it from that list. So what we've done over the years, we've developed a graphical technique called combinational polygon. I don't know if I put it on the list. Oops. Have I missed one off? 1 and 2, 1 and 6, 2 and 5. Have I done it wrong? Should it be a 5, should it? Sorry, well spotted, it's my writing there. Okay, 2 and 5, 2 and 6. Is that okay now? Yeah. I'm glad to see that tea breaks woke you all up. So we call it a combinational polygon. So there you are. So we've done the implication table. So what we do in a combinational polygon is you imagine a circle and we put the 6 states on the outside of a circle and we just draw together point to point all the states. And to get the groupings, every member has to be able to be combined with each other. So for one state, for example, 1 and 2 just need to be combined. But for 3 states, say 1, 2 and 3, 1 and 2 have to be combined and everything else has to be combined with the others. But you can see it. Graphical is easy. Looking at that table is more difficult. So best to do it in pictures. A combinational polygon. So imagine a circle. We'll just put the dots around the outside. 1, 2, 3, 4, 5, 6. So what we do now, if my list is correct or the table is correct, we just transfer those connections that are possible together. So 1 to state 2, 1 to state 6, I hit it, 2 to 5, 2 to 6, 3, 4, 5, 6, 3 to 4, 3 to 5, 3 to 6, and 4 to 5. That's it. So now you can see, and with a bit of experience, after 2 minutes you'll see how to do it. So you could still say, and all the groups have to be unique. You can't have members in 2 groups. If you're inexperienced, you might say, okay, I'll take state 1 and 2, and 3, state 5 and 4. That's eliminated 3 states. Okay? So what you're looking for is anything connected on a line is okay, a triangle for 3, and like a to go on. So can you see triangles in there? 2 triangles are there, aren't we? So what we're going to choose as our best combinations are these 3 and the bottom 3, because we're all connected to each other in that group. So that means we get down to only 2 states. How good is that? Only 2 states from 6. So it means 1 can be combined with 6 and 2, 2 can be combined with 1 and 6, and 6 can be combined with the other 2. If one of these links is missing, you can't do it. And doing it graphically is a lot easier than looking at this. Okay, we'll just carry on. We don't need lights. So we'll say underneath, combine one, 2, and 6 into a new state 1, and combine 3, 4, 5 into a new state 3. Okay. So we can now do revised state tables under here. Okay, so slightly trickier than last time. We now reduce 6 rows into 2. So anywhere we had a 1, 2 or a 6, we're now going to rewrite as a 1. So we'll do that first. So that's still there. Put it on the first row. That 2 becomes a stable state and the new 1. That 1 is there, comes from that 6. Then the transition is now a 3. Okay, and the output will be 0, 0, 1, and that dash on the transition. So that's the first ones, and 3, 4, and 5, that's the middle section. That 3 stays as a 3. The stable state 4 becomes a 3. The stable state 5 becomes a 3, and that 1 is still there as a transition. So we've got 1 dash 0, 0. So 2 things to notice there. Very cool, we got 6 states down to 2. Good for us, you know. Means the design's faster, less gates, and so on. And you got stable states there, 1 and 3, and you should notice we've got different outputs in different columns. That's allowed. So for example, stable state 1 and the inputs are 0, 0 or 1, 0, the output's different. That's allowed, but you can't have them in the same column. So final thing to do with design is to do the Carnot map. Sorry, to assign the secondaries. Secondary state assignment's very easy. We've only got 2 states. You only need 1 secondary, only a single Y term. So I'll draw that. This trajectory just shows, as we said yesterday, the transition between the states. So if you're in state 1, you can only go to state 3 in this new reduced table. If you're in state 3, you can only go back to state 1. So they just have y equals, I said 0, and y equals 1. It's up to you as the designer to decide which one is 0 and which one is 1. And you could decide to try the design both ways, see which comes out with a minimum gates. So in this case, looking at the outputs, both stable states have 2 outputs at 0 and 1 output at 1. So this choice is pretty arbitrary. So there's no real reason for doing this, but you've got to make a decision. Life is about making decisions. You can't make decisions, you can't move on. So I say 0, 1. If you just said 1, 0, it's still valid. Okay? So it's a secondary state assignment. So we're nearly there. So finally we just need to put all that information, change these tables, input the secondaries in and the secondary input down the side into like pseudo Carnot maps, and we can design the circuit. So the output's just the same, but these sort of unspecified states we now convert into don't care states in the output map to make our life easier, make the groupings bigger. In this one, everywhere we see a state 1, doesn't matter if it's transition or stable state now, we're going to call it 0. So we fill in a number of zeros. And then everywhere we had a state 3, we're going to assign binary 1. Okay, so you're all experts now at Carnot maps. So we know we've got a group of 2 there. There's no groups of 4 that I can see. Have I made a mistake there? That should be a 1, I think. Yeah, I've made a mistake in my transcription. This should be a 0, I'm sorry about that. And that should be 1. Okay. I think that's correct, so that's 3, 3, 3. So over 3's a logic 1 and over 1's a logic 0. Okay, we've got it. So now we can take the groupings. So you've got a group of, you can have the 2 corners. You've got to take that corner with this corner. That's that one. Take those 2 together. So that's Y. Not X1. Or X naught X1. That's where the grouping's from. So the final thing we can see in the inputs, we've got a gap if we jump between these 2 groups, so we put this static hazard joining group in, which should be YX north. And that's done. You all okay with that? You're a very good class. Take the rest of the day off. Sorry. Right, so I'll draw the circuit for you just as an exercise so we can see how we draw it with 2 secondaries, sorry, 1 secondary. Pardon? Okay, yeah. What I'll do, I'll take this one off, yeah? I'll draw the circuit, and I'll leave the circuit up there, and I think we can have a 5-minute break because for the faculty member coming in after me. So I'll put the circuit up, so when you've taken it down, if you need to stretch your legs, you can. If not, we'll start again in, say, 5 minutes after I finish. But otherwise... This one? I'll do it now, yeah. From here, yeah. What we're doing is, in this one, we're merging together states 1, 2, and 6 into the top. Yeah? So think of row 1, row 2, and row 6. Everything that was a 1 has been relabeled. So everything that's a 1, 2, or 6 has been relabeled a 1. So that's the obvious one, yeah? 1 into that. This stable state 2 is being merged together, pushed. So this is a stable state in this box. We're renumbering it a 1. Okay? This one isn't necessarily the same as this one, it's just naming. And state 6 is there, so we're renaming that a 1 in that box. And that 1 there is being merged, the transition state is being merged with a stable state. So the output stays in the stable state. The other one that's missing is this one, because this is now state 1 here. This is a 3 that takes us into the other state, which has got a unspecified. On the other side, you've got rows 3, 4 and 5, we're merging these. So we start with 3, which is the easy one. That stays in the same place. The output stays naught. 4 is being squeezed together there, so that 4 becomes a 3 in that row, and the output stays naught. It's 2 noughts anyway. And the final one, 5 is here, so that becomes a 3, and 5 is an output of 1, so 5 is there. And the transition back is via this 6. This 6 is now 1 to take us back. It's complicated. Just if you look at it in detail, basically we're squeezing 3 rows into 1 each time. So it's a good saving. So by doing that, we're saving 4 states. Are you okay now? If you don't follow, you can ask me any time. You know, I'll be here tomorrow morning, the next day. Okay, so I'll that is 2 input OR gate. Where the feedback path going through, so you've got uppercase Y becoming lowercase y. Label all these gates, you can see where the connections are. So, Y coming back. just done it as an example. You don't need to draw it because you can work it out for yourself from the equations now. You know, say earlier, if you had schematic capture, you could enter that in. If you had some other system, you might want to enter the equations in different ways of entering nowadays, different systems. So are there any questions? No? Okay, so tomorrow, there's another faculty member coming in about now. We'll have a break, a short break if you want one. We're going to look at hazards and races very quickly, but two with examples. So two design examples where things